Welcome to DBMS lecture. In this lecture we are going to see about the advanced topics. First topic is distributed databases. Under the distributed databases we are going to see about the architecture of distributed databases, data storage in distributed databases, and transaction processing, query processing, and optimization. First, distributed database system definition. Database that store data across multiple physical or logical locations. Data are distributed among many locations and we can access data from everywhere. That is known as the distributed databases. The architecture of distributed database allows scalability, fault tolerance, and improved performance. That are all we are going to see. First, characteristics. Scalability. Scalability means handle large amount of data and high numbers of concurrent users. Next, fault tolerance. It is nothing but data is replicated or distributed across multiple nodes. The system can continue to function even if some nodes fails. Third one, improved performance. Improved performance means by locating data closer to end users or application latency or end users or application latency can be reduced. The data transfer, amount of data transfer is known as that can be reduced. Geographic distribution, it is also one of the characteristics. These are all also advantages of distributed database system. Load balancing. Balanced workload can be carried out so that we can avoid the bottlenecks, maintaining overall system performance. At last, data replication. These are all characteristics and advantages. Next, challenges and considerations of a distributed database system. Data consistency, partitioning, network communication, complex management, and data security. Data consistency means maintaining asset property is very complex in the distributed database system. So consistency, try to maintain the consistency property. Partitioning, how to partition data have significant impact on performance and scalability. That factors we have seen in the characteristics slide. Communication, rely heavily on network communication between nodes because the network issues can affect the performance. Complex management, due to the involvement of multiple nodes and data, synchronization issues can be possible. Security, crucial to prevent unauthorized access and data breaches. It is very challenge one. Okay, architecture. Three different types of architectures are present. Client server architecture, peer-to-peer, multi-DBMS architecture of distributed database management system. In client server, one system acts as a server and another system acts as a client. Client includes the interface. Server means it will provide functions such as data management, query processing, optimization, transaction management, etc. Peer-to-peer, all systems will act either as a client or a server. Multi-database management system, it is integrated database system that the previous architectures are integrated and form a collection to form two or more autonomous database systems. This is the architecture diagram. Client 1, client n. From that end user application programs can be run. From the server, the database services can be accessed through the communication manager. Like that, some protocols can be used. Peer-to-peer architecture, every one can act either as a client or server. External schemas are present at top, global conceptual schema, under that a local conceptual schema and internal schema are spread. Multi-database, in this autonomous systems, integrated autonomous systems are present. According to that, a local view, internal view, like that we can distribute the views. Next topic we are going to see about the data storage in distributed databases. Data storage, it refers to how data is organized, partitioned and stored across multiple nodes in the distributed system. Okay, what is the goal of this efficient data distribution? Improved performance, fault tolerance, scalability. The characteristics of distributed database systems are going to be achieved through this. Then the key aspects of data storage is data partitioning. That can be two strategies are present for this. Range based partitioning, hash based partitioning, like that partition can be done. Replication enhances availability and fault tolerance can be reduced. What are the strategies? Means master slave replication, multi-master replication. Then after that, consistency models determine how data changes propagate across replicated nodes. What are the models or strategies? Eventual consistency, strong consistency, casual consistency. After that, data location, storing data closer to where it is most frequently accessed. Then data distributor strategies, it depends on data size, access pattern, system requirements. At last, backup and recovery are supported. Then security and encryption are the key aspects of data storage. Next, in distributed data storage, two concepts are very important. One is replication and fragmentation. Assume some relational database model. That system maintains multiple copies of data stored in different sites for faster retrieval and fault tolerance. For that, we are going to use the replication. Next, fragmentation. Different fragments are partitioned and stored in different sites. Replication and fragmentation can be combined. System can maintain several identical replicas of each such fragment. Okay, we are going to see in detail about the replication. Replication means copying, that is the many copies are made. If replicated, if it is stored redundantly in two or more sites. If one data is available more than one site, means that is called as the data replication. Full replication of a relation is the case where the relation is stored in all sites. That is meant as full replication. Fully redundant databases are those in which every site contains a copy of the entire database. Two terms we have learned. First one, full replication. Next, fully redundant database. What are the advantages of replication? Availability. If one site failure means we can approach another site and we can pick the data. That is the availability. Parallelism. Parallelly work process can be done. Reduced data transfer. Which site is nearby, from that we can access the data. These are the advantages. Disadvantages means increased cost of updates. We want to update in each and every site where that data resides, and it also increase the complexity of concurrency control. One solution for this is to use the primary copy. We will see about that in the later slide. Then data fragmentation. We are going to fragment data. That is, we are going to divide relation R into R1, R2 up to Rn that contains sufficient information to reconstruct relation R. This can be in two types: horizontal fragmentation, vertical fragmentation. In horizontal fragmentation, each tuple, that is one row is assigned to one or more fragments. Vertical fragmentation, the schema, that is the column, the schema for relation are split into several smaller schemas. All schemas in these two conditions are met or to be met. All schemas must contain a common candidate key or super key. For ensuring the lossless join property, then special attribute, otherwise for uniquely identification we have to maintain a tuple id attribute. This is the example of horizontal fragmentation. For horizontal fragmentation, row wise, we are going to use the select branch name hillside of account. In account to query, select branch name is equal to value view of account. Okay. In vertical fragmentation, schema wise we have to maintain the fragmentation. For that we are going to use the project branch name, customer name, tuple id of employee information, that is the record name. Here also deposit to is equal to project of account number, balance, tuple id of record information, employee information. Okay, what are the advantages of fragmentation? Horizontal allows parallel processing, and then the relation can be splitted up so that the tuples are located where they are most frequently accessed. In vertical, tuple id attribute along with a candidate key, one unique approach. For uniquely identification, we will use the tuple id that will allow efficient joining of vertical fragments. It also allow parallel processing. In this, it allows tuples to be split so that each part of the tuple is stored where it is most frequently accessed. In horizontal, a tuple is located where they are most frequently accessed. In vertical, it allows the tuples to be split so that each part of the tuple is stored where it is most frequently accessed. This is the main difference among between the advantages of horizontal and vertical. These both can be mixed. Fragments may be successfully fragmented to an arbitrary depth. Wherever necessary, we can use that approach. Distributed transactions. Transaction may access data at several sites. There are two persons are available. At each site, a transaction manager is available who is responsible for maintaining a log and for coordinating concurrent execution of the transaction. Next, transaction coordinator, who starts and allocate the works to the transaction managers. At last, he will terminate each transaction process and coordinate the works. Okay, system failure modes. Failures unique to distributed system. If a site is maintained by transaction manager and coordinator. If a site is failure, means loss of messages can be occurred, then communication link can be broken. Due to that, network partition can also occur. Network partition and site failures are same. For that, we are going to use the commit protocols. Two commit protocols are available, 2-phase and 3-phase. 2-phase is most widely used. 3-phase is used wherever the critical applications are available. To overcome some of the drawbacks of 2-phase protocols, that are all we are going to see in the upcoming slides. Okay, for what purpose we are going to use the commit protocol? Means to achieve the atomicity. Atomicity means all or none, all updates. Means all transactions, all steps of the transaction should be done, or otherwise none of the steps should be done. 2-phase commit protocol assumes fail stop model. That means failed sites simply stop working and do not cause any other harm. That is fail stop model. The execution of the protocol is started by the coordinator. and the works are distributed among the transaction managers. Local sites are involved. Let T be the transaction initiated at site SI, and let the transaction coordinator be S at SI be CI. Phase 1, obtaining a decision. Phase 2 is recording the decision. While obtaining a decision, coordinator asks all the participants to prepare to commit the transaction. This message is added. Prepare of T to the log. That is also saved in the stable storage, permanent storage. Okay. For this, prepare of T message is sent to all sites at which our transaction is executed. Upon receiving the message from the coordinator, transaction manager decides if it can commit the transaction or not. If not committed means no T is added to log and send abort message to coordinator. Otherwise, if the transaction can be committed means ready T to the log is sent and folds all the records to the stable storage. Okay, after this, recording the decision. For recording the decision, ready T message received from all the participant sites that are to be committed. Otherwise, no ready T message means aborted. According to this, coordinator adds a decision record to the stable storage. Coordinator sends a message to each participant informing it of the decision. Participants take appropriate action locally. Okay, handling of site failures. If a site failed means it will be recovered by using the log. Log contain commit of T means redo operation performed. Abort of T means undo of operation performed. Ready T means, if log contain ready T means site consult coordinator to determine the fate of the transaction, whether to undo or redo. The log contains no control record means concerning to certain transaction replies the site failed before responding to the prepare T statement. Before sending the prepare T statement itself, that site will be failed. In that situation only, no control records are present in the log. In that situation, failure of site precludes the sending of such response. Coordinator must abort the transaction and execute the undo operation. No prepare T is sent means coordinator abort the transaction and undo operation is performed. If a coordinator is said to be failed means the commit two-phase commit protocol executes according to the 4 conditions. First one, if an active site contains commit T means the transaction must be committed. If an active site contains abort T means the transaction must be aborted. If some active participant does not contain a ready T record, then the failed coordinator cannot have decided to commit T, can therefore amount. Because the coordinator itself failed, so ready T is also not available for that site means in that situation abort only performed. If none of the above cases are held means no additional control records are present for the particular site means for a particular transaction. In that case, active sites must wait for coordinator to find the decision. Okay. Next, network partition. Due to the network partition, if failure occur means coordinator and all its participants remain in one partition, the failure has no effect on the commit protocol. If all are present in one partition means no effect on the commit protocol. If the coordinator and participant belong to several partitions means then sites that are not in the partition containing the coordinator think coordinator has failed and execute the protocol to deal with failure of the coordinator. According to the failure of the coordinator situation, it will act. No harm results, but sites may still have to wait for decision from coordinator. Harm results will not be produced during this criteria, but time will be taken. The coordinator or sites in the same partition means coordinator think that the sites in another partition have failed and follow the usual commit protocol. Again, no harm results. Next, recovery and concurrency control. In doubt transaction, if you have a ready T in log but neither commit or nor abort, then recovery site must determine the commit or abort status according to by contacting other sites where it have done the transactions. Like that, it have to refer other sites. This is the recovery algorithm. The recovery algorithm mainly carry two steps. Instead of ready T, write out ready T comma L. L means list of logs held by the T where the log is written. For every in-doubt transaction T, all the logs noted in the ready T comma L log record are reacquired. After log reacquisition, transaction processing can resume. The commit or rollback of in-doubt transaction is performed concurrently with the execution of new transaction. According to that transactions done by that particular operation, we can decide whether it can commit or abort. Next, we are going to see about the three-phase protocol. In this no network partitioning, at least one site must be up. At most case sites can fail. Phase 1. In phase 1, obtaining preliminary decision, it is similar to two-phase where each site is ready to commit if instructed to do so. Under two-phase protocol, each site will wait for decision from coordinator. Under three-phase protocol, here one keyword we are going to use, pre-commit. Knowledge of pre-commit decision can be used to commit despite coordinate failure. We have no need to worry about the coordinator failure. Pre-commit keyword is present in log means we can further proceed. In phase 2, recording the preliminary decision, coordinator adds a decision record, whether it is abort or pre-commit, in its log and forces it to stable storage, similar to the two-phase protocol. Coordinator sends a message to each participant informing it of the decision. Participant records decision in its log. If abort reached, then participant aborts locally. Locally abort will be done. If pre-commit decision reached, then participant replies with the acknowledgement T. This is the second phase. Third phase, recording decision in the database. It is executed only if decision in phase 2 was to pre-commit, not abort. In this, coordinator collects acknowledgements. After pre-commit, we are going into the step of acknowledgement. So coordinator collects the acknowledgement and send a commit T message to the participants. Coordinator add that into the log and saved in the stable storage, and the message is passed to each participant. Handling site failure. Since site failure, if log contains committee, same redo operation. Abort means undo operation. Ready T only present but no abort or pre-commit means we will consult the coordinator to determine the fate. 3 conditions. First one, if coordinator says T aborted means undo operation. If coordinator says T commit means executes redo. If C says coordinator says T committed, site resumes the protocol from receipt of pre-commit T message. Then recording of the pre-commit in the log is checked and acknowledgement is received, or whether the acknowledgement is sent or not is also recorded. According to these 3 conditions, coordinator will decide the fate of the transaction. Continue. Handling site failure continue. Next situation is if log contains pre-commit of t but no abort of t or commit of t, coordinator once again coordinator is going to determine. Abort means undo, commit means redo. If coordinator says t is still in pre-commit state, site resumes protocol at this point. Then if log contains no ready t means for a particular transaction, site executes undo, then directly do the abort t record. If coordinator failure means, here we are using pre-commit, that is one advantage in comparing to two-phase protocol. The active participating sites will select a new coordinator. New requests local status of t from each participating site. After requesting, it will receive the response. According to the response, commit, aborted, ready, pre-committed, not ready, these status will be received. Each participating site record sends its local status to CNU. In this, all statuses are recorded in the stable storage. If a site that failed and required must ignore any pre-commit record in its log when determining its status. Only for pre-commit only we have to give some attention. Okay, then CNU will decide either to commit or abort T to restart the three-phase commit protocol. Commit means commit, abort means abort. Pre-commit means two cases. Pre-commit message is sent to those participants in the uncertain state. Protocol is resumed from that point. If any uncertain state is present for all live participants means, then only abort is done. At least n-k sites are up. The fact that all participants are in an uncertain state means that the coordinator has not sent a commit T message, implying that no site has committed the T. Next, concurrency control. For distributed environment, how we are going to modify our concurrency control schemes, we are going to see about that along with the commit protocols. Single lock manager approach. In single lock manager approach, single chosen site is taken. When a transaction needs to lock a data item, it sends a lock request to that particular site, and lock manager determines whether the lock can be granted immediately. If yes means, lock manager send a message to the site which initiated that request. If no means, request is delayed until it be granted, at which time a message is sent to the initiating site. In this, the transaction can read the data item from any one of the sites at which a replica of the data item resides. Write must be performed on all replicas of a data item. What are the advantages? Simple implementation, deadlock handling can be simple, but disadvantages are bottleneck vulnerability. During write operation situation, we have to write in all the replicas. Distributor lock manager. In this approach, lock manager at each site will be present to provide the lock. Lock managers control access to local data items, but special protocols may be used for replicas. What are the advantages? Work is distributed and can be made robust to failures. Disadvantage, deadlock detection is more complicated. Lock managers cooperate for deadlock detection. That is very complex situation. For this approach, many variants are present: primary copy, majority protocol, biased protocol, quorum consensus. These are all we are going to see. Primary copy, we have to choose. Already we have seen this term primary copy. One replica of data item is selected as a primary copy, and that site containing that replica is called as the primary site. Different data items can have different primary sites. When a transaction needs to lock a data item queue, it requests a lock at the primary site of the queue. Implicitly, lock is provided. What is the benefit of this? Concurrency control for replicated data handles similar to unreplicated data. Simple implementation. This is the benefit. What is the drawback? If the primary site itself fail means queue is inaccessible. Even though other sites are having the data item, we are not able to access. Next, majority protocol. In this local lock manager at each site administers lock and unlock requests stored at each site. When the transaction wish to lock an unreplicated data item queue, then the message is sent. If queue is locked in an incompatible mode, then the request is delayed until it can be granted. When the lock request can be granted, the lock manager sends a message back to the initiator indicating that the lock request can be granted. This is the majority protocol. In case of replicated data, how the situation is handled. If queue is replicated at n sites means, then half of the n sites to the half of the n sites the lock request should be sent. When the transaction does not operate on queue until it has obtained a lock on a majority of the replicas of queue. Majority should be obtained. When writing the data item, transaction performs write on all replicas. So what is the advantage? Can be used even when some sites are unavailable, because we are sending the lock request not only to only one site but to majority of the sites. Next, drawback. It requires 2 into n by 2 plus 1 messages for handling lock requests, because majority lock should be sent, and n by 2 plus 1 messages for handling unlock requests, potentially for deadlock even with single item. Each of the three transactions may have locks on 1 by 3rd of the replica of a data. So deadlock is not able to recover. Next, biased protocol. Local lock. Here also local lock manager available at each site, similar to majority protocol. Shared locks are differently handled. Shared lock means only read can be performed. When a transaction needs to lock a data item, simply request a lock on queue from lock manager at one site containing a replica of queue. That is the shared mode. In the exclusive lock, when transaction need to lock data item queue, it requests a lock on queue from the lock manager at all sites containing a replica of queue. Shared means only one replica is enough, but in exclusive means all replica of queue. Advantage is imposes less overhead on read operations. Disadvantages, additional overhead on write. That's all. Next, we are going to see about the timestamping. Timestamping based concurrency control protocol that can be that can also be used in distributed system. Here, local timestamp, global timestamp, two timestamps are used. Local timestamps are generated by using local counter or the local clock in the system. Global unique timestamp is obtained by concatenating the local timestamp with some unique identification. A site with a slow clock will assign some smaller timestamps. Serializability not affected, but disadvantages on transactions. How to fix this problem? With each site a logical clock, that is denoted as LC, which generates the local timestamp, requires each site to advance its logical clock. Whenever a request is received from a transaction with the timestamp x, y, x is greater than the current value of logical clock, then only that will work. In this case, site SI advances its logical clock to the value xi plus 1. So the x value is generated depending upon the logical clock. Next one, Multi-master and lazy replication. Multi-master replication means we can update anywhere. Updates are permitted in any replica. Any replica is updated means all replica will also get that update. It is coupled with two-phase protocol. Next, lazy propagation, where updates are transmitted after transaction commits. If some sites are disconnected from the network also, the updates will be performed. The cost of consistency is very high in lazy propagation. Okay, deadlock handling. This is one example of deadlock which cannot be detected locally. First one in transaction T1, write of x, write of y. X lock is provided on x means y has to wait. In transaction 2, y is provided exclusive lock means x has to wait. How it can be solved? By using some graphical method, a global wait for graph that is constructed and maintained in a single site. The deadlock detection coordinator will present for maintaining the global wait for graph. Here real graph, constructed graph, two types of graph are available. Real but unknown state of the system. Constructed graph means approximation generated by the controller during the execution of its algorithm. State is done approximately. The global wait for graph can be constructed by using the global wait for graph is constructed under three situations: when a new edge is inserted or removed from the local wait for graphs, or a number of changes have occurred in a local wait for graph. The coordinator needs to invoke cycle detection. In that situation, global wait for graph is constructed. If the coordinator finds a cycle, then it notifies all the sites as a victim and the rollback will take place. This is one example. Local transaction local graph is developed. Local wait for graph T1, T2, T5, T3, and another group is T2, T4, T3, site 1, site 2. From this the global is drawn, combining site 2 and site 2. Unnecessary rollbacks can happen that may result when deadlock has indeed occurred or a victim is picked. In that situation, only rollbacks are happen. That is undo. We have to abort that situations and we have to return to the previous cases. Okay, next topic is distributed query processing. For the query processing is in distributed system is very complex. The cost of a particular strategy is the number of disk accesses that is maintained as a cost. Other issues means data transmission over the network, then having several site process parts of query in parallel. These are also taken into account. Okay, query transformation. For obtaining the optimization, we can transform the query. Here see in example account 1, we are going to select the hillside. In account 2, value view side. Next in optimization, we can union these two queries so that we can reduce the time and cost. In this example, only tuples pertaining to hillside branch is taken. We can eliminate the selection operation on the value view side. So this expression cannot be possible because hillside value view side empty only returned. We can avoid this type of queries to improve the optimization. Next, join processing. We can join multiple relations. Here we are going to see some examples. Account, depositor, branch 3 relations that are stored at site S1, S2, S3 respectively. If a query issued at site 1, the system need to provide the result at site 1 itself. What are the possible query processing strategies? We can ship means transfer, copy all the 3 relations to site 1 because we want the result in site 1, and choose a strategy for processing the entirely locally at site S1. Otherwise, we can ship a copy of the account relation to site 2 and compute a temporary relation that contains account and depositor joined at S2, and temporary 1 from S2 to S3, compute temporary 2 is equal to temporary 1, branch at S3. We are going to merge these relations and putting in some temporary relations. Likewise, the strategies can be developed. By using this, we also consider the factors such as how much data must be shipped, cost of transmitting a data block between sites, relative processing speed at each site. These are all to be considered, and if these are satisfied means we can transfer. Next, semi-join strategy. If R1, that is a relation with the schema R1 stores at site 1, then R2 be a relation with the schema R2 stores at site 2, means we can evaluate the expression R1 semi-join and obtain the result at S1 itself. For computing this, temporary relation is developed by projecting both schemas at site 1. Then we have to transfer temporary 1 from S1 to S2. After that, we have to compute the temporary 2 relation. In that, we are going to join relation 2 with temporary 1. Then we have to transfer it from temporary 2 relation to S1. After doing all this, at last we can compute the R1 semi-join temporary 2 at S1 itself. That is similar to R1 join R2. The semi-join can be denoted as like this. Join is join symbol, semi-join symbol, one side it will not be closed. These join strategies will also exploit parallelism. How if 4 relations are joined means, and we can take the result from site 1 by shipping different. Here in this situation, R1 is shipped to S2, R1 join R2 is computed as S2 simultaneously, R3 shipped to S4. How R3 and R4 are joined, computed at S4. Okay, only 2 sites are available in participating, S2 and S4. S2 ships tuples of R1 join R2, S4 ships tuples of R3 join R2. Both are shipped to S1. Once the tuples R1 join R2, R3 join R4 are arrived at S1, we compute join for both of these in parallel, and so that we can get the result in S1 itself. Query processing. It is a heterogeneous database, distributed database. The schema translation should be done because a global schema should be developed. For that, we have to write a wrapper for each data source. Wrappers must also translate updates on global schema to updates on local schema. Limited query capabilities are only available because some data sources allow only restricted forms of selections, example web forms, flat file data sources like that. Queries are to be broken up and processed partly at the source and partly at a different site. If we want to remove the duplicate of information when sites have overlapping information, then a global query optimization is considered. Okay, what are the performance optimization means? Key value stores do not provide a declarative query language. We have to use the join, aggregate, etc. on their own. Then we have to avoid the complex running times for joining. If the running times are very complex, means we have to avoid that. Application code maintains some materialized view queries. For example, if a user makes a post, the application made some add some summary to that post, like that. Materialized view can be added. Many key value stores allow related data items to be stored together. We form an entity group according to that post. We can make a groups. Other functionalities means stored procedures or versioning of data can also be helpful for optimization. Okay, then query optimization. uh, it is also can be done in equivalent trees like join or order, otherwise using operators. Estimated cost calculated on input output CPU utilization based on statistics. Lowest cost will be chosen at last. Search space must be larger because this is a distributed database. Must select sites for joining relations. Must select method for shipping inner relation, whole or matches, which are matching conditions that are only picked out. This will minimize the resource utilization. What is mean by ship whole or fetch matches? Ship whole means inner relation at home site. Any single table predicates, like that we can ship whole. Whole can be shipped, not a problem for space. Fetch matches. Outer tuples which are only projected on a particular column can be chosen. Which columns are useful for us in our query, according to that we can choose. Not like shipping whole. Fetching matches can be chosen and projected, matching the tuples back. Next, dynamically. A temporary index can be created on the inner relation. Then we can ship inner relation, store in a temporary table and index temporary. Just we have seen about that temporary relations of joining and semi-joining, like that only. Semi-join, projected outer relation on join column, where we can eliminate the duplicates. Then we can produce it as an inner relation to the particular result producing site. After that we can compute the natural join and ship matching tuples back. Then that relations can be joined. At last, bloom join. This idea is the same as semi join, but instead of sending all values in the join column, so it filters some of the false positives through collection techniques, and selected values are chosen under inner join. That's all about the query optimization techniques and distributed data storage architectures of distributed database management. Hope you had understand. Thank you so much.